Welcome, everyone. So in class, we looked at our list of elementary functions and saw when they're continuous. They're continuous on their domains. We looked at how you can figure out their domains. We also saw that you can take these different pieces here and combine them in different algebraic ways. So you can add them, subtract them, multiply them by a constant, multiply and divide, and the result is still going to be continuous, with one little possible exception there. You just got to be careful, no division by zero. All right. Well, there's one other algebraic way we can combine functions that's a little bit different than just plain addition, subtraction, multiplication, division. And that is composition, taking two functions and composing them. So this is a little bit different. And this is going to be a recurring theme. Composition, we're going to see that when we get to derivatives, we're going to be talking about composition of functions. When we get to integration, we're going to be talking about composition of functions. So this is going to be something we come back to. We're going to start, though, first of all, what is composition of functions? And then we're going to see how it works for continuous functions. So just a little practice. The way we indicate taking two functions and forming their composite function, the notation we use is this little circle, this little open circle. So we read this f composed with function g. And what this does is it produces a brand new function. And the formula for that function is f with g of x plugged in. All right, so when we look at this, a lot of times we're going to consider g of x the inner function. You'll probably hear me say this. So it's the thing we plug into the other function, and you can probably guess function f, that's going to be called the outer function. So big surprise. So that's the thing that happens on the outside. So you can think of composite functions almost as like layers. There's different layers to your function. Now in the notation, the outer function is what we write first. The inner function is the one we write second, just in that little terminology. Now, how you can think of this is, let's start with a function. And when we start with a function, we take our input x. And for a composition, we kind of work, in the formula here, you want to start at that x, and we're going to kind of work our way out. So we take x, we take our input x, and we're going to plug that in to our function g first. So g is the inner function. G is the thing that we plug our input into first. So you can imagine the function is like this little device, this little machine, this little box here. And what it does is it spits out, it returns a brand new thing, which we call g of x. So for function g, you take your input x, you plug it into the machine, and you get out g of x. Well, what the composition does is it takes that new input and then it plugs it into the next function. So you can almost think of this as like an assembly line. So then it takes g of x, and the conveyor belt keeps going, and we plug it into function f. And what that does is that returns our final input, or our final output here of this function. So this is our final output here, and it's f with g of x plugged in. So we have our input x, we have our final output here, and the way to think of the composition is you can think of it as just kind of grouping these two, kind of viewing this entire process as just one formula. So the composition is just this entire process here. So this is the composition. F composed with g of x, or F composed with g. So what it does, you can think of this whole thing as just some magic box here, magic function, where we take x, pretend you can't see into this thing, just a black box. We take input x, plug it into this composite function, F composed with g, and then it spits out its own output. But we can actually zoom in and see kind of the inner workings. It first goes into function g, then it goes into function f. All right, so let's get a little practice. So let's try an example here just to see how composition works. So we're going to calculate f composed with u, and our function f of u is the arc sine function, or inverse sine of u. And then our u of x function is this 1 minus square root x over 1 minus x. And we want to calculate f composed with u. So again, f is going to be the outer function, and u here is going to be the inner function. So when we start this, let's write out. We want to calculate, we're going to plug u of x into function f. All right. So the idea here is if we look at our function f, figure out wherever its variable is. So in this case, function f is inverse sine of u, and there's our variable. So sometimes you might have more than just the one variable, but in this case we just have that one variable. And our inner function, the formula for u, is this whole fraction. So the idea is we're going to take this whole piece here, and this is our u value, and we're going to plug it in to that outer function. So we end up, when we do that, arc sine, or inverse sine. Normally it's just arc sine of u, but we're going to replace u with what u of x actually is. It's this whole fraction here. So this is going to be inverse sine of, or arc sine, of 1 minus square root x over 1 minus x. So I identified where my inner function is, and then I just replaced all instances of variable u with what u actually is. So we calculated this composition. Now it turns out, why we're bringing this up with continuous functions, just to get a little practice, this is another way to combine two functions that's not just simple addition or subtraction. Well, for continuous functions, if your inner function and your outer function are continuous, well, the result when you form their composition is going to be continuous as well. So that's what the result says here. So composition works really nicely with continuous functions. And probably our most useful result from this is that if the outer function f is continuous, then what we can do is, if we're trying to calculate the limit of f of some inner function, some composite function like this, as x approaches a, then we can essentially take this, take that whole limit, and we can essentially move it through the continuous function. So in a way, we can think of this as, first we can figure out the limit of the inner function, see what we get there, and then once we figure out that result, just plug it into the outer function. So you can think of this as just taking the limit sign and moving it inside the continuous function. Now this only works if that outer function is continuous and this limit that of the inner function is actually a number in the domain of that function. All right, so let's try an example. See how this would work. So let's look at that composite function we just did. So we've got inverse sine or arc sine, kind of just synonyms there, of this 1 minus square root x over 1 minus x. And we know arc sine, inverse sine, is a continuous function on its domain. So we're doing the limit of this entire thing as x approaches 1. So what we can do, because inverse sine or arc sine is continuous, we can use continuity. So our outer function is continuous. So what we can do is, rather than calculating the limit of that entire thing, we can instead calculate first the limit of just that inner function. So 1 minus square root x over 1 minus x. We can calculate that limit. And then once we figure out what that inner limit is, then we can just plug that result into the arc sine function. Now, before we actually even get to this point, going back, probably the first thing to try is, because this is just all elementary functions, it's a composition, we've got inverse sine, we've got some square roots and subtraction, we're dividing. First thing to try is just direct evaluation. Before we even start messing around with this continuity. So let's try direct evaluation. And if we were to try that, let's see what we get. So we're plugging x equals 1 into the entire thing, and we end up with 1 minus square root 1 over 1 minus 1, and that's no good. We've got 0 over 0 there. It's undefined. So this is what the expression would look like, except that's undefined, so we're kind of stuck. So it's kind of a dead end. 0 over 0 is not the answer. We can do better than that. So we're going to keep going. So now we're going to use the continuity of that outer function. So rather than calculating the limit of that entire thing, we're going to move the limit inside that arc sine function, and we're going to focus on just the limit of that fraction. And let's do that off to the side. Let's do that. It's going to take a little bit of work. So let's do this one off to the side. And you might be thinking, how are we going to do this? And we've learned one of our special little algebra tricks. So it should kind of pop in your head when you see square roots getting added or subtracted to some other term. And that trick, if you remember, is to multiply by a fancy one, to multiply by the conjugate of the term. So we're going to take that same, we're going to rationalize the numerator here. We're going to take this term, and its conjugate is, we just change that minus to a plus. Okay? And then we want to multiply by a fancy one, so we have to make a fraction, same thing in the numerator as in the denominator there. Let's multiply the two denominators together, and we won't multiply them out. So let's just leave it as 1 minus x times 1 plus square root x. And we saw with some of the examples we did with this conjugate method, when you multiply out these conjugate terms, this is just essentially a difference of perfect squares. So you could go through and multiply it all out, but what you get is you end up getting, if you look at this negative term here, you get the first term squared minus that second term squared. So the first term squared is just going to be 1. Then we've got minus, and if we square the square root of x, we're back to just x. So we end up with a 1 minus x in the numerator. Now it's good practice, especially if you're a little rusty. Try multiplying this out, this term with this term, but this is what you should end up with, 1 minus x. And now we see that The 1 minus x shows up in both spots, so we can cancel that out in both places there. And what we're left with then is just the limit of x approaching 1, 1 over 1 plus square root x. All right. So now, as soon as we do that canceling step, we want to try direct evaluation again. And this time, it's going to work. So we try it again. Direct evaluation at x equals 1. And in this case, when we do that, we get 1 over 1 plus square root 1, which is 1/2. So now we can go back up. And now we know what the limit of that inner function was. So we can fill that in. And 1/2 is in the domain of arcsine. So this is our answer. And we can go back. If we want to check it out, inverse arcsine here, if we go back up to our table, let's check the domain of inverse sine. There it is. 1/2 is inside that interval. So if we had calculated the limit of that inner function and we found that the limit was 2, well then the limit of that composition would not exist. We can't plug something into inverse sine if it's not in the domain. But in this case, the limit of that inner function worked out. All right. So I want to try example 8 here. I want to finish this up. So I want to figure out, kind of like what we did when we looked at just algebraic addition, subtraction, multiplication, division, that type of algebra, figured out where a function was continuous. Now I want to see how to figure out where a composite function is continuous. So what we're going to do here, just like we did before, is figure out essentially the domain of these different functions. So we want to figure out for each of these the domain of continuity. All right, so let's start with the first one. We want to figure out where this function sine of x cubed, what its domain is. All right. So we want to get the domain of this function h of x. So the idea is we want to break this apart into, we want to look at this composite function and we want to identify what the inner function is and what the outer function is. So the inner function is, well, the stuff inside the parentheses usually. So our inner function here is going to be this sine x. The outer function is the stuff, well, outside. It's the outermost layer of the function here. So our inner function, we'll call that u of x, is the sine function. And our outer function, we'll call this our, careful how you say it, our f of u function. And that's going to be just the cube part. So we'll kind of swallow up that whole inner function, and we'll just call that whole inner function just a u. So this will be u cubed. All right, so now let's look at these individual pieces. First of all, we've got our inner function. So what's the domain of this inner function? And the domain, if we remember, we can go back to that table if we need to. For sine and cosine, anything's fair game. So the domain of sine is all real numbers. It's the interval from minus infinity to infinity. So it's all x values. Okay. And just to be careful, when we're looking at our inner function here, I've used the variable x. And then for the outer function, which is f of u, I'm using the variable u. So when I say the domain is all real numbers, these are x values that I'm talking about. Now, if we look at our outer function is u cubed. This is just a polynomial. So let's figure out the domain of that. And the domain of u cubed is, again, all real numbers. It's a polynomial, so there's no issues there. But now, the domain, these numbers, refer to variable u. So these are all u values. So it's almost like you want to think of these as like different universes. We've got our x universe, and then we've got our u universe here. All right, so what we have between these two, domain of our inner function, there's no restriction, so everything's good. Our outer function, again, there's no restriction, everything's good. So what we're going to see is basically anything is fair game. So to help visualize that, let's go back to our assembly line analogy here. So let's suppose that we're starting with input, and I'm going to need a little bit more room, so I'm just going to slide this up real quick. All right, so let's start with our assembly line analogy. So let's take input x, and we're going to plug it in to this function. So the very first thing that would happen is we're going to plug x into the sign piece. So we're going to plug this into our inner function, which we've called u. And when you do this, at this point you want to think, is there any restriction on what x values can I actually plug in? So you want to think, is there any restriction at this point? Nope. I can take any x value and I can plug it into function u. No problem. Okay. So what do I get out when I do that? Well, I get sine of x. So now I want to take sine of x. If I keep going on the assembly line, I want to take sine of x, and now I want to plug that into my function f. I want to plug it into the cube function. So I'm going to take this, and we're going to plug it into our function f, our outer function. And at this point, you want to think, is there any restriction on sine values that I have to make before I can plug it into function f? Well, sine of x, well, actually I can just go right here and I see that, no, I can plug anything that I want into function f. But at this point this is another point where you want to ask, are there any restrictions here? You know, it's conceivable maybe sine has a value that I can't plug into my outer function. But in this case, nope, no restrictions. So at the end of the day, when I take sine of x and plug it into that cube function, I end up with my composition, which is sine of x cubed. So because there's no restriction at any of these points, all of those x values that I tried from the very beginning kind of make it through from each of the different stages. So my initial x value makes it through all of my possible x values here make it through the u filter, and then I get sine of x, and then all of those values make it through the f filter there. So I can essentially plug anything in. So there is no restrictions for this one between these. So that means because there's no restrictions, all of my x values work. So that means the domain of h of x is all real numbers. All right, so let's try one where there is some restriction. And we're going to look at the next case here. Our function's called capital F of x, and our function is natural log of 1 plus cosine x. So first thing we want to do, again, this is not just regular addition, subtraction, multiplication, division. This is a composition. So you want to kind of break apart the different, kind of peel off the different layers of your function. And we want to start by identifying the innermost layer. So this is kind of the thing that happens to x first. And usually if you see parentheses, it's the stuff inside the parentheses. So I'm going to call that 1 plus cosine x, I'm going to call that my inner function, and I'll call it u of x. Now my outer function here, this is the next layer, and in this case it's the natural log function. So that's going to be my outer function. And I'll use the same notation, just little f of u. And this is going to be natural log of u. All right, so what's the domain of each of these functions? Well, for the first one, what's the domain of 1 plus cosine x? Well, the domain of the function 1, that's just a constant function, so all real numbers work just fine there. Cosine x also has domain all real numbers, and I can take two continuous functions and add them together, and I still get a continuous function. So all real numbers from the constant, all real numbers from cosine. So my domain here for this innermost function is going to be all real numbers. And again, these are this is my x value universe here. So when I say the intervals here, these are x values. So I don't see any restriction. So based on the inner function alone, there's no restriction on what x values I can plug in. So we're going to just kind of send x values through the assembly line and see which ones get stuck at any point along the way. That's kind of the idea here. So let's start our little assembly line. We've got our input x, and we're going to send it along its way. And we'll plug it into our inner function u. And at this point, we want to think, is there any restriction on what I can plug into function u? And based on the domain we found, no. We're good at this. We're good at this stage. So are there any restrictions there? Nope. All right, well then that's going to spit something out. And in our case here, that spits out 1 plus cosine x. And then we're going to want to plug that into that result into our, we're going to send it to the next machine, which is going to be our function f, our outer function. And we want to think, are there any restrictions here? All right, so we're trying to take 1 plus cosine x, and we want to plug it into natural log. Well, first let's figure out what is the domain of natural log. Domain of the natural log function, if we go back up to our list, we can't plug negative numbers in, and we can't plug 0 in. So the domain is 0 to infinity, open interval. And when we talk about this interval, this is all u values. All right, so what is the restriction? There's no restriction here, so any x value we plug in is going to make it through this function, this part of the assembly line, no problem. But now, as that x value keeps going, this is where it might run into some issues. Because 1 plus cosine x conceivably could be negative, or it could be 0. And that's going to kind of put a wrench into the I'm going to keep going with this assembly line. Could gum things up here. Could slow down our could break things. All right. So what's another way? What's another way to think of this? Well, this interval, what it's really telling us, what this restriction says, is that we need our u value to be greater than 0. So there is some restriction at this point. So anything that I take and I'm trying to plug into function f, I need it to be greater than 0. So we do have some restriction here. This one we do. So what is it? Well, the restriction, I normally need u to be greater than 0. But if we fill in what u actually is, u is my 1 plus cosine x. I need that whole thing to be greater than 0. And so we have to figure out where this inequality happens. Or maybe let's figure out where could this inequality not be true. So rather than trying to figure out where this inequality is true, let's figure out where it can go wrong. And let's look at 1 plus cosine x being equal to 0. So we know we can't have this thing equal to 0 because that's going to kind of break things at this point. But let's just see if this even happens. So if we try solving this equation, what we end up with is, let's get cosine x by itself. So we get cosine x is equal to -1. And then if we figure out where cosine x is equal to -1, if we remember back to our graph, cosine x only bounces back and forth between -1 and +1. So all of those -1 places, these are the kind of the odd multiples of pi. So those are the places where cosine x is equal to -1. So pi, 3 pi, 5 pi, 7 pi, all the odd multiples. If we think about what the graph of 1 plus cosine x would look like, it's going to look like our regular cosine curve, just shifted up 1 unit. So because cosine x is always bouncing back and forth between -1 and +1, that means 1 plus cosine x is always going to be bouncing back and forth between 0 and 2. So for most of the time, this inequality is going to be satisfied. The only time it's not is when 1 plus cosine x is equal to 0 in this case. And those are the odd multiples of pi. So putting it all together, the domain of this function, we could write, call it capital F here, is going to be the interval. So it is going to be most of the x values. So most of the x values, if you tried plugging them in, would make it all the way through. Oh, and let's just finish our assembly line there. We end up with natural log then of 1 plus cosine x. So most of the x values you try plugging in. So if you plug in, say, x equals 2, it's going to make it through here, no problem. It's going to make it through here, no problem, and then you'll get your thing. But if I tried taking x equals pi, it's going to make it through this part, no problem. But then I end up with 1 plus cosine of pi. Cosine of pi is -1, and 1 plus -1 is going to give me 0, and I can't plug 0 into natural log. So pi is going to break the machine at this point. So I can't plug pi in. Same thing at 3 pi. 3 pi is going to make it through this whole part, no problem, but then I'm going to end up with natural log of 0, which breaks the machine here. So most real numbers are going to work. I just have to throw out these odd multiples of pi. So we'll write this. We won't be super precise the way we write this. I'm just going to write this little kind of set theoretic subtraction sign, and we're going to remove just the odd multiples of pi. All right. So a little technical, but the main kind of takeaway here is just getting to work with composite functions and being able to identify the inner function, the outer function, and just keeping an eye on where those inner functions and outer functions might be undefined and where you might run into issues along the way. All right, so we're going to stop there. And maybe we'll see how we're doing on time. We got a little behind today, so with all the excitement, maybe we'll try another one of these in class though as a little practice. All right, we'll see you then. Bye bye.